So question number 12. The zero sequence current of generator for line to ground fault is J2.4 per unit. Then the current through the neutral during the fault is. So here what they have given the zero sequence current as J2.4 per unit, and the nature of fault they have mentioned as line to ground fault. Now we are aware that for line to ground fault all the three sequence networks they are connected in series. So if this is the positive sequence network, then negative sequence network and zero sequence network. So all these three networks they are connected in series like this. If we assume a dead short circuit, because fault impedance is not mentioned, so directly dead short circuit if we assume, then it will be connected directly as a short circuit here. So this is the positive sequence reactance X1, negative sequence reactance X2, zero sequence reactance X0. Then the positive sequence current is IA1, the negative sequence current is IA2, and zero sequence current is IA0. The positive sequence voltage is VA1, the negative sequence voltage is VA2, and the zero sequence voltage is VA0. So this is our source voltage, let us say VF. Then we can write here that all the three networks are connected in series. So IA0 will be equal to IA1 will be equal to IA2, and by Ohm's law we can write this as VF divided by X1 plus X2 plus X0. Now this current we have given directly as J2.4 per unit. In terms of per unit they are given. What is asked? The current through the neutral during the fault. Now we know that whatever fault current is there, that is phase to ground current, so same current will flow through the neutral. So the fault current, that is the neutral current, we know it will be sum of IA0 plus IA1 plus IA2, because as a standard convention we assume the fault on phase A. So if we assume the currents as IA0, IA1, IA2, then the total current, fault current in phase A will be IA0 plus IA1 plus IA2. Now here as we can see all the three currents are equal. So neutral current or the fault current will be equal to 3 times IA0. So we should remember this relation. The fault current or the neutral current, it is 3 times the zero sequence current, or positive or negative. Anyhow they are same. So our answer will be IN equal to 3 into IA0. So IA0 is J2.4 unit. So IN will be J times 2.4 into 3, that is 7.2 per unit. IN will be equal to J 7.2 per unit. So out of these 5 options, correct answer will be option C. So what you have to understand that all 3 sequence networks, they are connected in series for line to ground faults. This question it is on line to ground. Moving to the next question, question number 13. So which one of the following statement is not correct regarding bundled conductor? Now this question is asked in engineering services exam year 2021. So option A, voltage stress at the conductor surface is reduced by using bundled conductor, which is quite true. We have seen that the voltage stress or potential gradient is inversely proportional to the size of the conductor, and in bundled conductor size is increased. So if size is increased, the stress, voltage stress, it will reduce. So this is actually the important advantage of bundled conductor. Next, corona loss is smaller by using bundled conductor, that is also correct. So corona loss, it is inversely proportional to size. So more is the size, smaller will be the corona loss, because potential gradient or stress is reduced, therefore corona loss will reduce. Option C, current carrying capacity is decreased in bundled conductors as compared with a single conductor of equivalent cross section area, which is not true, because if we use the bundled conductor, we are using more than one conductor per phase. For example, if we use 2 conductors, then like this. So this is R phase, Y phase and B phase. Now if we use two subconductors per phase, then obviously current capacity it will be doubled as compared to a single conductor, because there are two parallel paths. Like if we use four subconductors per phase, current carrying capacity it will become 4 times. So therefore this is not true, and it is asked which is not correct. So the option C is not correct. Coming to option D, the line having bundled conductor is less liable to cause radio interference. That is also advantage, because the size is increased, so potential gradient is reduced, corona loss is reduced, and consequence of that is that radio interference it will be reduced. So option C is not correct. All three, option A, B, D are the advantages. We are asked not correct, so correct answer will be option C. Now moving to the next question, question number 14. The sag of a transmission line with 50 meter span is 1 meter. What will be the sag if the height of the transmission line is increased by 20%? Now what they have mentioned, that height is increased. Now whether the effect of height take place on a sag, we can see this from the equation of sag. Now we have seen the sag is given by WL square upon 8 in case of equal level of support. In this particular equation, nowhere there is a presence of term height. So we can say sag is not a function of height of tower. It is not a function of height of tower. So therefore, whether height is increased or decreased, the sag will remain same. So therefore, even if height is increased by 20%, the sag will remain same. So answer will be, if previous sag or original sag is 1 meter, even after changing the height, sag will remain same as 1. Moving to the next question, question number 15. A distance relay with inherent directional property is known as. Again, this question is asked in Engineering Services Exam 2016. Option A, Buchholz relay. Option B, admittance relay. Option C, directional overcurrent relay. Option D, directional switched relay. Now if we see the first, Buchholz relay, it is basically a mechanical relay. It is used for the protection of transformer against the internal faults, and it operates on the mechanical principle. So it is a kind of a mechanical relay. So it is not correct. Option B, admittance relay, so which is quite correct. The admittance relay, which is also known as Maho relay, it possesses the inherent directional property. If we see the characteristic of a Maho relay, it will be like this, a circle which is passing through the origin. This is the characteristic of Maho relay, Rx. So inside this, if fault impedance falls within this, then relay is going to trip, and outside this, relay is going to rest. Okay, so commonly there are three relays, that is the impedance relay, then reactance relay and Maho relay. Out of these three, the Maho relay, that is the admittance relay, is the only relay which has the directional property, and we are talking about distance relay. Okay. Now option C, if we check, directional overcurrent relay, as the name itself says, it is a directional, therefore it will possess a directional property, but it is a overcurrent relay. And the question is on distance relay, so this option is not correct. Directional switched relay, which is also not correct because it is not a distance relay. So correct answer, it will be admittance relay or Maho relay. Admittance relay, another name is the Maho relay, which possesses the directional property. That is actually the advantage of Maho relay. Now moving to the next question, number 16. The sequence components of the fault current are as follows. The positive sequence component is J2 per unit, negative sequence current is minus J0.5 per unit, and zero sequence current is minus J1.5 per unit. The type of fault in the system is 3-phase fault, single line to ground fault, double line to ground fault, double line fault, and 3-phase to ground fault. Now we need to understand how the sequence networks are connected for each type of fault. Now for 3-phase fault, as it is a balanced fault, 3-phase fault and this one, 3-phase to ground fault, these two are balanced faults, and for balanced fault, the current flowing through each phase, it will be same. So current flowing through phase A, it will be same as current flowing through phase B, which will be same as current flowing through phase C. I am talking about the phasors. They will be displaced by 120 degree. Okay, so magnitude of each current, it will be same. The phase angle will be 120 degree, and we know that for balanced system only positive sequence component will exist. Okay, so IA1 it will be present, whereas IA0 it will be 0, and IA2 that is negative sequence current, it will be 0. So IA0 stands for 0 sequence current of phase A, IA2 stands for negative sequence current of phase A, IA1 stands for positive sequence current of phase A. So IA0 and IA2 it will be 0. So here there is a presence of positive and 0 sequence, therefore first option is not correct. Now coming to the second option, SLG fault. So I will write here. So SLG fault, just now we have seen that all three sequence networks are connected in series, and for series we know that current will remain same. So IA1 equal to IA2 equal to IA0. If this is the condition, then we can say that the fault is single line to ground fault. But here as we can see, IA1, so I positive means IA1, I negative means IA2, and I0 means IA0. So all these three are not equal, so therefore it is not a single line to ground fault. Coming to the next, double line to ground fault. Now how we can determine whether it is double line to ground fault? For that we have to understand how the sequence networks are connected in case of double line to ground fault. For double line to ground fault, all the three networks are connected in parallel. So this is positive sequence, then negative sequence, and zero sequence. All these three networks, they are connected in parallel. Okay. So this current, it will be IA1. This current is IA2, and this current is IA0. If we assume the fault impedance as 0, then directly they will be connected in parallel. Okay, so VA1, VA2 and VA0 all are equal. VA0 equal to VA1 equal to VA2. And if we apply the KCL at this node, all three are incoming. So IA1 plus IA2 plus IA0, it will be equal to 0. So this is the condition for double line to ground fault. So this is first three-phase fault. So this is second SLG, single line to ground. This is double line to ground fault. Now we can check IA1 plus IA2 plus IA0 whether it is 0. So IA1 is J2, IA2 is minus J0.5, and IA0 is minus J1.5. So if we add these three, it will be 0. So this particular set of sequence network currents are for double line to ground. So correct answer, it will be option C. So A and E are not correct because balanced fault IA0 and IA2 should be 0. Here they are not 0. Single line to ground fault, all three sequence network current should be same, but here they are not same, therefore this is also not correct. Now what about option D, that is double line fault? So in case of double line fault, the sequence network are connected as follows. When there is a double line fault, no zero sequence current will flow. So IA0 is 0. So this zero sequence current, it will be 0. So it is not connected. So IA0 is 0. And the remaining two sequence networks, that is positive and negative sequence networks, they are connected in parallel. So this is the positive sequence network, and this one is negative sequence network. They are connected in parallel to each other. So this current is IA1, whereas this current is IA2. What is relation between these two? So IA1 will be equal to minus IA2, or IA2 is minus IA1. Then that particular fault is double line fault, and IA0 should be 0. So here this condition is not satisfied, so this option is also not correct. So remember the sequence network connection for each type of fault. So here correct answer, correct option, it will be option C. Now moving to the next question number 17. Lightning arresters connected in power system protect electrical equipment from. 5 options are given. Option A, frequency fluctuation. Option B, overcurrent due to indirect lightning stroke. Option C, over voltage due to indirect lightning stroke. Option D, direct stroke of lightning. Option E, all the above options are correct. Now which option is correct here? Now the lightning arrestor, or it is also known as a LA or surge arrestor, it is the first element in any substation. It is connected in parallel with the power system and it protects the equipment against the indirect lightning stroke and whatever over voltage is created due to the indirect lightning stroke. So correct answer it will be option C. Now, direct stroke of lightning, which equipment is going to provide the protection against this direct stroke of lightning? So here whatever ground wires or earth wire we are connecting at the top of the tower, so this wire, it will protect against the direct stroke of lightning. If lightning take place nearby, then due to that there will be over voltage. In order to protect the equipments against that over voltage, we are using the lightning arrest. So correct answer will be option C. Option B also they have mentioned indirect lightning stroke, but they have mentioned overcurrent. Whereas whenever lightning take place, the main effect it will be over voltage. Obviously over voltage will be created due to overcurrent itself, but it is a over voltage protection device. Remember, lightning arrestor is over voltage protection device. Whatever circuit breakers are there or fuses are there, all these are the over current protection device. The frequency fluctuation, the lightning arrestor cannot do anything regarding the frequency fluctuation. So correct answer will be option C. Question number 18. Following is true for HVDC system. Option A, skin effect present but absence of charging current. Option B, presence of charging current and no skin effect. Option C, both are present. Option D, both are absent. Option E, proximity effect and skin effect is present. Now we know that in case of HVDC system, that is high voltage direct current system, there is no skin effect, there is no proximity effect, there is no charging current. Why there is no skin effect? Because for DC system, your inductance it will be 0, and if inductance is 0, then skin effect it will be 0, absent. Proximity effect it will also be absent, right? Now why skin effect is absent? Because XL is 2 pi FL. So here we can write more properly XL, inductive reactance, as 0, and frequency for DC is 0. So therefore XL it will be 0. And if inductance is 0, the current will be uniformly distributed throughout the conductor surface. So therefore skin effect will be absent and there will not be any effect of current flowing through the other conductor on the resistance of a particular conductor. Therefore proximity effect will also be absent. Now, what about the capacitance? So capacitance is present only at the starting when we are switching the line. Otherwise capacitance will also be absent. So Xc is 1 upon 2 pi Fc. So frequency for DC is 0. So Xc it will be infinite. So infinite means it is a open circuit, like a open circuit condition. So if there is an open circuit, there is no question of charging current. So no charging current will flow. So there is no skin effect, no proximity effect, and no charging current. Okay, so correct answer it will be both are absent. So that is the advantage of HVDC. Remember, in case of HVDC system, inductance is 0, capacitance is 0. If capacitance is 0, no charging current. If inductance is 0, no skin effect and proximity effect. Resistance will be present, but resistance for DC it will be less as compared to resistance of AC because of absence of skin effect. Because in case of AC system, resistance due to skin effect it will increase about 40 to 60% more as compared to the DC system. So all these are the advantages of HVDC system. Corona loss will be present in case of HVDC, but comparatively it will be less. Radio interference will be also comparatively less. Question number 19. So in general, power factor can be improved by using a power factor we can improve by using shunt capacitor. So combination of capacitor and inductor in parallel, which is not correct. Combination of capacitor and inductor in series, which is not correct, because whenever we use the inductor, actually power factor it will be reduced because inductor absorbs the reactive power, whereas capacitor supplies the reactive power. So we should not use the inductor for improving the power factor. Sometimes we connect the inductor in series with the capacitor just to minimize the inrush current that capacitor may take. But in general, we don't connect capacitor and inductor in series to improve the power factor. Correct answer will be shunt capacitor. Now series capacitor. Why we are using series capacitor? Series capacitor is used to reduce X, to reduce the line reactance. Effective line reactance, we use the series capacitor, and if we reduce the line reactance, the power transfer capability it will increase, because power transfer capability it is given by Vs VR by X sin delta. If we use the series capacitor, then X it will be XL minus XC. So this XL minus XC it will get reduced. That is denominator get reduced. Therefore, power transfer capability will be increased. The power factor will be unchanged. Here they are asking the power factor can be improved by using. So series capacitor is not correct. Shunt inductor, that is also not correct. Shunt inductor, why we are using? To minimize the Ferranti effect. Many times during no load or light load condition, the receiving end voltage will be more than the sending end voltage. In order to avoid that, in order to reduce that, we use the shunt inductor. Where we use series inductor? So to limit the fault current, to limit short circuit current or fault current, sometimes we use in a power system series inductor. Okay, because fault current it is inversely proportional to the reactance. So if we increase the reactance, fault current it will be reduced. We cannot connect series resistance because of the size, and its loss will be very huge. Continuously current will flow, it will cause a huge loss, and it will be large heating device. Therefore, in order to limit the fault current, we connect the series inductor. Here they are asked how power factor can be improved. We can use the shunt capacitor. Question number 20. If the fault current is 5 kA, the relay setting is 50% and the CT ratio is 200 by 5 ampere, then plug setting multiplier will be. Now, if you see the connection, how relay is connected, if this is the transmission line, there will be a CT, and CT secondary we are connecting to the relay. Now the CT ratio they have given as 200 by 5 ampere. The fault current, somewhere there is a fault in the system, and the fault current that is flowing in the system is 5 kA, that is 5000 ampere. Then we have to determine the plug setting multiplier, PSM. What is the expression for PSM? Plug setting multiplier is a ratio of relay current flowing through the relay divided by plug setting, PS. Plug setting, PS. So this is the formula for PSM. Now how much is I relay? Now if 200 ampere is primary current, secondary is 5 ampere. So what will be the secondary current if 5000 ampere is a primary current? So we can write 200 corresponds 5, then 5000 corresponds how much? So it will be 5000 into 5 divided by 200. So 0 will get cancelled. Here it will be 25 into 5 it will be 125 ampere. So here during the fault, current flowing through the relay coil it will be 125 ampere. So numerator is 125 ampere divided by plug setting. Now how much is the plug setting? They have given as a 50%. So plug setting is 50%. 50% of what? 50% of rated current. Now how much is the rated current of relay? So relay rated current can be 1 ampere or 5 ampere. So it depends on how much is the rated CT secondary current. So CT secondary current rated is 5 ampere. So plug setting is 50% of 5. 50% of 5 it will be 2.5 ampere. So plug setting is 2.5 ampere. So 125 divided by 2.5 we can write as 1250 divided by 25. So it will be 50. Okay, so PSM will be 50. So 1 to 4, that is 50 times the plug setting value the current is flowing when the fault current is 5000 ampere. So remember this equation, PSM is a ratio of I relay upon plug setting. Thank you.